Hi guys, so welcome to a new video on differentiation under Math SL. In this video we should focus on problems of optimization problems. I shall solve the three questions that are on the screen in front of you, and I shall begin with question 1 short. So the first question that we shall tackle came in paper 1, November 2017, question number 6. Kindly take a minute to attempt to solve, and the answer shall follow through shortly. So we are given that f of x equals 15 minus x squared. So for any value of x, the corresponding y value shall be 15 minus x squared. So for example, if x were 1, then the f of x value when x is 1 shall be 15 minus 1 squared. This is important in context of this problem. The following diagram shows part of the graph of f and the rectangle OABC, where A is on the negative x-axis. So O is fixed and A is moving on the negative x-axis. So the distance between O and A shall always be x, because A is on the x-axis. So if A is at the point negative 3, then the distance between the 0 and the negative 3 is 3. Or negative 3. Now, I am required to find the x-coordinate of A that gives the maximum area of rectangle OABC. So, the hardest part in this problem is just to visualize the curve and understand that the width of the rectangle is given by x, and the length of the rectangle is given by the distance from point A to point B, which shall always be the y value at B, which is given by 15 minus x squared. This is the tricky part of the problem, understanding that the horizontal distance is x and that the vertical distance is represented by 15 minus x squared. Hence, the area of the rectangle can be given by x times 15 minus x squared, and we want to find this maximum area. So we want the x value that maximizes this area, and of course we know that the maximum value of y is given by y dash equals 0, as in turning points and curves and so on. So the maximum value of the area shall be given when a dash equals to 0. We can easily obtain a dash from a, so what I've done here is I've expanded the red equation to get the blue equation, which is still the area, 15x minus x cubed. Then I've differentiated the area to get an equation for a dash. Now, if I want to get the maximum value of a, as we said, I shall set a dash to 0. Hence, the green equation is set to 0 and the values of x are obtained. X squared equals 5, hence x equals positive or negative root 5. So which is it? Is it the positive root 5 or the negative root 5? From the graph, we can tell that since a is on the negative x-axis, I shall choose negative root 5 as the x-coordinate of A that shall give the maximum area. So this concludes the first problem on optimization. Take a minute to write this down if you will, and I shall begin question 2 shortly. So the second question that we shall tackle in this video came in paper 1, November 2005, question 15. Kindly take a minute, attempt to solve, and the answer shall follow through shortly. So we are given that the following diagram shows a rectangular area ABCD enclosed on 3 sides by 60 meters of fencing and on the 4th by wall AB. So we have a fence that encloses this side, and this side, and the perimeter of this fence is 60 meters. And the 4th side is enclosed by a wall, so this is not relevant to us. Now you can choose to pick the length as the longer side or the shorter side, and the width vice versa. That is entirely up to you. This will change the answer. So if you decide that this is the length and this is the width, this should change your final answer, especially that they are requiring the width. So you should give them the length instead. But the convention is that the longer side is what we call the length. So watch out, because your final answer, if you follow the same model that I have, shall be 15. However, if you switch the L and the W, you shall get a final answer of 30. So watch out. Both are considered correct. So anyway, we shall move on with the conventional model. You are given that this is the length, this is the width, and the perimeter of 3 sides equals 60. So W plus L plus W equals 60. And we want to find the maximum area, knowing of course that the area is equal to the length times the width. But we cannot maximize the area, we cannot get A dash if it is represented in 2 variables. So we cannot have the area in terms of both L and W. So what we need is to get one variable in terms of the other. We shall do this using the green equation right there. L plus 2W equals 60, hence L equals 60 minus 2W. So since L equals 60 minus 2W, we can rewrite the area in terms of W only. So W times L becomes W times 60 minus 2W, which gives us 60W minus 2W squared. Now, given this area, I can easily get the maximum area by getting A dash and setting it to 0. So A dash should be the derivative of the red function, which is 60 minus 4W, which is equal to 0. Hence, solving this equation, I get that W equals 15. So this concludes our second question. I hope you have found it easy to understand. Pause the video to write this down if you will, and I shall begin the third question shortly. So the third question came in paper 2, November 2009, question 7. Kindly take a minute, attempt to solve, and the answer shall follow through shortly. So we are given that the area of this rectangle is 525 meters squared. We are given that the fencing used for this side costs $11 per meter, and the fencing for the other 3 sides, this one, and that one, costs $3 per meter. We want to find the minimum cost, so we want to minimize the cost. Hence, we shall need to get an expression for the cost of fencing. Now, since the area equals L times W, which is equal to 525, I can get W in terms of L, so that when I get the expression for the cost, I don't have 2 variables. I can get the expression in 1 variable only. So, as we said, the cost shall be given by 3L plus 3W plus 3W plus 11L. So, how did I get that? Simply because this side costs $11 per meter. So, if the length is 2 meters, then it shall cost 11 times 2. If the length is 5 meters, it shall cost 11 times 5. If the length is L meters, then it shall cost 11L. Similarly, for this side, it costs $3 per meter to fence. So if this side is 1 meter, it shall cost $3. If it is 2 meters, it shall cost 3 times $2. If it is W meters, it shall cost 3W. This applies as well to this side. It shall cost $3 times the width, whatever the value of the width is. And finally, for the fourth side, it shall cost $3 times the length, because this is a length, not a width, and it costs $3 per meter to fence. Hence, this side shall cost me 3L to fence. So the total cost is given by 3L plus 3W plus 3W plus 11L, which is given by 14L plus 6W. As we said before, we cannot have two variables representing the cost, so we need to write one in terms of the other, which is why we went back to the equation of the area to get W in terms of L, so that we can remove this W and write it in terms of L, as in right there. So the cost is given by 14L plus 6 times 525 over L, or you can actually do the multiplication on the calculator. 6 times 525 gives you 3150 L to the power of -1. Now that I have an expression for the cost in terms of one variable only, I can get C dash and set it to 0 as we've done before. So C dash, of course, the purple equation is the derivative of the green equation, and we've set it to 0. Now we need to solve for L. You can either do this manually or using the GDC, whichever you'd like, but anyway, you shall find that L equals 15. The manual attempt is right there, so the algebra of it is right there, but of course you can use the GDC to maybe sketch the curve and find the 0 or something of the sort. So now that we found the value of L that minimizes the cost, we plug it into the equation of C in order to get the minimum cost. So we shall plug this value of L into the equation of C, not C dash. The equation of C and not C dash, so the green equation. So I've plugged the 15 into the green equation, and this gives me a cost of $420. So take a minute to copy this down if you will. This concludes our third question and our video. I hope you have found it useful.